This lecture continues from the previous one where I talked about frequentist statistics to contrast it with Bayesian statistics. See the other video first to learn about frequentist statistics. Frequentist statistics gives you the probability of your data given that the null hypothesis is true, as I went over in the last video. Bayesian statistics, on the other hand, gives you the probability of your preferred hypothesis being true, given that the data that you obtained, the results that you obtained, is true. Bayesian statistics is actually older than frequentist statistics. It was developed by the 18th century English statistician, philosopher, and Presbyterian minister, Thomas Bayes. And it's a much more nuanced version of statistics than frequentist statistics. And it makes a lot more intuitive sense once you kind of get the hang of it. Because it is more complicated and more nuanced, it is more in line with the way that scientists actually think when they are conducting experiments and interpreting their results. Bayes developed the theorem that you see in front of you on your screen, and which I will describe in detail. I am going to use this example, which comes from the citation that you see here on your screen. I've updated this example to make it about COVID-19, but the example from this website is very similar. So let's say that a person is not feeling well, and so they go get a test for COVID-19. What is the probability of a person having COVID-19 if the test that they take comes back positive for the disease? These are hypothetical numbers here. These are not real numbers. I am not an epidemiologist, so I don't have the up-to-date numbers and the most accurate numbers about these different probabilities. So this is just a hypothetical example that I'm using with COVID-19 to make it more applicable to what's going on in the world right now. But these numbers are made up. So consider the following information. At any given time, 1% of the people in the population everywhere in that area have COVID-19. 5% of the time, a person who takes a test for COVID-19 will get a positive result on the test even though they do not have COVID-19. This is a fact that you may not have been aware of. Tests for COVID-19 have a false positive rate. There is a certain percentage of people that will take a test for COVID-19 and they will get a positive result even though they do not actually have COVID-19. The test is imperfect and it will pick up on some chemical in that person's body that shows a positive result even though that person does not have the disease and never has. Also consider if a person has COVID-19, the test will be positive 90% of the time. That's something else you may not have considered. Tests for COVID-19 are not perfect in that they can also give false negatives. Sometimes a person has COVID-19. They'll take a test for COVID-19, but the test will not pick up on the chemicals in their body that show that they have COVID-19, and the test will show that they do not have COVID-19. That happens 10% of the time. 90% of the time, a person who has COVID-19 will be registered as having COVID-19 by the test, but 10% of the time, 1 out of 10 times, the test will register that the person does not have COVID-19 when in fact that they do. And all of this information is important in Bayesian statistics. All of these different numbers that you see in here will be plugged into our Bayesian equation. So Bayes intuitively understood that science is an imperfect tool for understanding the world. Our measurement instruments for understanding the world do not work with perfect precision. Sometimes our instruments will tell us the wrong thing. And we have to take that into account when we take into account our new conclusions that we come to based upon our experiments. So here's the fundamental Bayes equation again. So we're going to start filling out what these different terms mean. So probability of A given B. This is the probability of a person having COVID-19 given that the test came back positive. Now you may think that if a person's sick and they go and get a test for COVID-19 and the test comes back positive, well, my oh my, that person definitely has COVID-19. But that is not the case, because the testing is not perfect. So this part of the equation here, probability of A given B, we don't know it yet. That's what we're solving for. The purpose of performing this equation is to solve for the probability of A given B. In this case, the probability that a person has COVID-19 given that the test came back positive for COVID-19. Our favored hypothesis, in other words, the hypothesis that we suspect to be true, is that the person has COVID-19. Probability of A given B is our favored hypothesis. That's the hypothesis that we suspect is true. Now, here, this part of the equation, the probability of B given A, that refers to the probability of the test coming back positive if the person has COVID-19. So this shows us our false negative rate. So given that if a person really does have COVID-19, how likely is it that the test is going to pick that up? It's 90% likely. There's a 10% false positive rate, so it's only 90% likely that the test will pick up that they have COVID-19. 90% is good, but it's not perfect. So that's what the probability of B given A is. The probability of A is the probability that the person has the disease. Now, this person thinks that they have the disease because they went for COVID-19 testing. But do they have the disease? They may not. So often the test will come back negative and the person actually really doesn't have COVID-19 either. But what is the probability that the person really does have the disease? Well, we know that 1% of the population at any given time has the disease. So our prior probability of the person having the disease is 0.01, which is, if you convert that to a percentage, is 1%. And our probability of B in this equation is, what is the probability that the test comes back positive? This requires some further calculations, because the test will come back positive sometimes when a person takes the test who has COVID-19, but occasionally the test will come back positive for a person who does not have COVID-19. So what is the overall probability if you give a test that the test is going to come back positive, whether or not the person has COVID-19? To figure that out, we have to go a little bit more in depth. 90% of the time, as I told you, the test comes back positive when the person has COVID-19. And 1% of the population at any given time does have COVID-19. 5% of the time, the test comes back positive even though the person does not have COVID-19. And 99% of the population at any given time does not have COVID-19. So, if you give a COVID-19 test, 1% of the time, you're giving that test to someone who has COVID-19, because 1% of the population has COVID-19. And 90% of the time, when you give the test to somebody with COVID-19, it will come back positive. So you multiply those numbers together. Now, 99% of the time when you give this test, the person will not have COVID-19, because 99% of the population at any given time does not have COVID-19. But 5% of the time, when you give that test to someone without COVID-19, the test will come back positive for COVID-19. So you multiply that number by that number, and then you add these two sets of numbers together. So at any given time when you give out a COVID-19 test, the probability that it's going to come back positive, whether or not the person has COVID-19, is going to be a little over 5%. So now we can simply multiply everything together. We already calculated in one of the earlier slides the probability of B given A. I'll take you back over there just to prove it to you. There we are. And we calculated that the probability of B given A is 0.9. And we've already calculated the probability of A. The probability of A is 0.01. And we already calculated the probability of B, because we went through all of these extra steps, and we came out with this number here. So now we simply plug those into the equation. This number we calculated to be 0.9. This number we calculated to be 0.01. And this number we calculated to be 0.0585. So when you plug this into your calculator, you get 0.15. So if a person takes a COVID-19 test and the test comes back positive, the probability that that person has COVID-19 is 15%. So in this example, with these fake numbers that I've put in, the probability of having COVID-19, if you take a test for COVID-19 and it comes back positive, the probability that you actually have COVID-19 is about 15%. That's a lot lower than you would have thought. Again, keep in mind, my numbers are fake. But in this fake example, the probability that you actually have the disease, if you get a test coming back telling you have the disease, is only 15%. In Bayes' theorem, this number here is called the prior probability. This was the percentage of the population that has COVID-19 at any given point. Posterior probability is what we are solving for. The posterior probability is the hypothesis that you think is correct. We have a person who's going and getting COVID-19 testing. The person wasn't feeling well, so we think that they have COVID-19. So we want to know, what is the probability that they really do, that they take a test that shows that they have COVID-19? What is the probability in that case that they really do have COVID-19? So that's the probability of our favored hypothesis. We think this person does have COVID-19 because the person wasn't feeling, the person went to go get a test. They got a positive test result. We think they've got COVID-19. What is the probability that they really do have COVID-19? That's the posterior probability. But here's another thing about Bayesian statistics. When it comes to the current situation, if somebody gets a positive result for COVID-19, they'll often be tested again. You see this happen at the White House, where the president is carefully encircled by people that have been shown not to have COVID-19 on these tests. But these tests are not perfect. So people are tested more than once. If someone comes up with a positive COVID-19 test, they'll be tested again. And Bayes' theorem is applied, because what happens when the person is tested again is this posterior probability becomes the new prior probability. The posterior probability becomes the new prior probability the next time we give the person a COVID-19 test. So the first time through we did the math, the probability of the person having COVID-19 given the positive result was 15%. Now, the next time we do the COVID-19 test, let's say they come up positive again. For that equation, we will now plug in this posterior probability as our new prior probability, because now the probability of the person having the disease has gone up from 1%, which was our best guess, because 1% of the population has the disease at any given time, to 15%. Because now we have a stronger belief that the person does in fact have COVID-19 because they already had a positive result. So our new prior probability is not as naive. Our new prior probability is 15%. Although you would express that as a probability, so it would be 0.15, not as a percent, which would be 1.5, just to make the equation work. Another important note, probability of B down here would not be altered. The only thing that gets altered the next time we run the equation, when we get the person tested a second time, the only thing that changes the second time is this prior probability. But the probability of B down here would still be calculated using these numbers here, our baseline for the population. So the only thing that would change would be the probability of A. Another note about all of this. If you are given an example of how to calculate Bayes' theorem, and somebody gives you some numbers, it can get very confusing looking at all of these letters and the given symbol and all of that. And it can make you want to plug in A here and try to divide it by B here, but that's not what you're doing. This is B given A. That's just a word. It's not B divided by A. This is not A divided by B or anything like that. So these letters can actually get in the way of applying Bayes' theorem. If you want to apply Bayes' theorem, you do the calculations the way that I showed you and forget about those A's and the B's and the given symbol, which looks like a divided symbol. Clear your mind of those symbols. And I think the best way to do that is to put in completely different symbols that have nothing to do with the letters A or B or A given B or anything like that. So think of Bayes' theorem as the probability of an elephant is equal to the probability of a zebra times the probability of a penguin divided by the probability of a hedgehog. And I know that seems absurd, but if you follow my steps, you'll find it much easier to apply Bayes' theorem. So the probability of the elephant is what we are solving for, and that's the probability of a person having COVID-19 given that the test came back positive. The probability of a zebra is the probability of the test coming back positive given that the person has COVID-19. Probability of a zebra, it's just a separate number. The probability of a penguin, that's the probability that the person has the disease. And the probability of the hedgehog is the probability that the test comes back positive. So then you just apply the equation the way that I taught you to apply it. And you don't think about dividing an A by a B or anything weird like that, because you don't do anything like that. Think about these terms as completely separate entities. Think about an elephant, a zebra, a penguin, and a hedgehog. You're not going to divide a penguin by a hedgehog or an elephant by a zebra or anything like that. Think about these parts of the equation separate and follow the rules that I've given you in this lecture to apply the equation. And then you just multiply the different parts together. You just multiply the probability of the zebra times the probability of the penguin divided by the probability of the hedgehog to get the probability of the elephant. Try it my way and you'll find that applying the equation becomes much easier. So that's Bayesian statistics. It tells you how likely any given hypothesis is if the data you gathered is true. So in this case, it tells us how likely it is that the person has COVID-19, given that they had a positive test for COVID-19. How likely is it that the person does in fact have COVID-19? Notice that Bayesian statistics, just built into the cake is this idea that you can repeat experiments and the probability, the posterior probability, the degree of confidence you have in your results will change every time you do the experiment. Every time you do the experiment, if you get the same outcome, your confidence in your hypothesis can grow. Just as I illustrated to you by showing you that the posterior probability of the person having COVID-19 becomes the prior probability of the person having COVID-19 the next time we give the person a COVID-19 test. So Bayesian decisions are not binary. You don't just run the experiment once. You run experiments again and again, and you take the results of the prior experiment and you use those to affect your degree of confidence in the experiment the next time you do it. In Bayesian statistics, you're looking for a posterior probability to be as high as possible. I know this is a lot to take in. Frequentist statistics is the probability of obtaining data like yours if the null hypothesis were true. Remember, the null hypothesis is the star of the show for frequentist statistics. Bayesian statistics is the probability of your favored hypothesis being true, given that the data is true. And what this means is that in frequentist statistics, you're looking at p-values, and if you want to find support for your hypothesis, you want to find a p-value that's as low as possible. So you want to be able to reject the null hypothesis as being unlikely by finding a p-value that's as low as possible. Bayesian statistics, you want the prior probability to be as high as possible. So if you're looking at the results of a Bayesian statistical test, you're looking for a prior probability that's as close to 1 as possible, because that would mean that your hypothesis is very likely to be true given the kind of data that you have obtained. So with frequentist statistics, the lower the p-value, the better. For Bayesian statistics, the higher the posterior probability, the better. Frequentist statistics is typically a one-off thing. You do your study, you obtain your results, you get your p-value, and that's that. Bayesian statistics is much more interactive. First, you do your study and obtain your results. You factor in the probability of various things. You compare the probability of the hypothesis being true at the end of your experiment, and that biases your experiment the next time you do it by changing your prior probability the next time you do the experiment, and so on and so forth. These prior probabilities that you plug into your equation the next time you do it, reflect your bias about what the outcome will be. The person tested positive for COVID-19 once. We now have a higher suspicion that the person has COVID-19. But with Bayesian statistics, you can also not bet in favor of a certain outcome. You can use something called equal priors, which means that no matter how previous results have turned out in other studies or the last time you did the experiment, no matter what, you can always keep the prior probability the same. So we could always keep our prior probability of the person having COVID-19 at 1%, in which case every time we ran the Bayesian statistics, the posterior probability would always be 15% if the person kept getting positive tests. You can run things that way. That's called equal priors or flat priors, and this is what most Bayesian statistical software does. So I wanted to point that out to you, that that's what Bayesian statistical software is usually doing by default, but you'll hear people say, oh, but you can change your priors if you want to when you run your Bayesian statistical analysis. So you can factor in previous experiments or previous studies into your Bayesian statistical test before you run it, which will influence the posterior probability that you get after running that test. So there you go. That's Bayesian statistics.